Let's take a few minutes to look at what it looks like to find the second derivative of an implicit equation. We're going to start out with x squared y equals x cubed, and we're looking for d squared y over dx squared. This is what we'd like to find, and we'll talk a little bit about that notation in a second. First, we need to find dy dx. That's always going to be step one. So we'll use a product rule. 1 d2 plus 2 d1 equals 3x squared. And if you're confused about where this came from, definitely check out the implicit differentiation video. I need to solve for dy dx. I'm going to do this pretty quickly in one step. So dy dx would be 3x squared, subtracting this term from both sides, minus 2xy, then dividing by x squared. So I have a dy dx equals 3x squared minus 2xy over x squared. Now, I want to find the derivative of this, but before I do, this is looking like it's going to be a lot to take the derivative of. If I can simplify it all, I want to do that. I'm going to divide this into two separate fractions. 3x squared over x squared is going to simplify to just 3, minus 2xy over x squared would be 2y over x. So just a little bit of simplification here goes a long way as I take the derivative of my new dy dx, which is 3 minus 2y over x. Now, I want to take the derivative of this with respect to x. Well, that's kind of where this notation comes from, right? D squared y over dx squared. And treating the differential as one variable with two letters, we can kind of drop those parentheses and just write dx squared. Equals, well, I need to take the derivative of this implicitly the same way I would have before. The derivative of 3 is 0, minus, and I have a quotient rule here, low d high minus high d low, which is just times 1, over the square of what's below. So I end up with the opposite of 2x dy dx plus 2y over x squared. Just taking this like -1 coefficient and distributing him through my numerator. And I'm almost done. I almost am finished. But my original problem was in terms of x and y, so I want to get my final second derivative in terms of x and y. And so I got to substitute for dy dx with what I know dy dx to be. Dy dx is 3 minus 2y. So I get -2x times 3 minus 2y over x plus 2y over x squared. And now I can treat this second derivative the same way I would treat any other second derivative, any other sort of f double prime of x, if you will, from a previous chapter, a previous part of a chapter, where I can use all the good things about the second derivative. I can apply those here as well. It's just now my second derivative is based on x and y instead of just an x value. That's what makes this an implicit equation. It makes this a little bit trickier to get through to a second derivative.